Welcome back, guys. This is our lecture on electric current, which we call electricity. Let's get started. So, up to this point, we've built two big historical experiments. We had the capacitor, which we charged by shocking, and we got a negative plate and a positive plate. A bunch of electrons that we've added on one plate, and a lack of electrons in the other that were pushed away by the electrons in the other plate. Then we created, most recently, the battery, which does, through a chemical reaction, constantly gives us a negative plate and a positive plate. Whereas before we had to charge it with friction, and it was very frustrating to do so. But batteries and capacitors are incredibly similar. Two metal plates separated by a material. And they both store electrical energy by creating high voltage across plates. So step one to understanding electrical current, which we call electricity, is to understand voltage, because voltage causes electrical current. Okay, taking a look at capacitors and batteries one last time. Once we have a negatively charged plate and a positively charged plate, all right, in our capacitor we said after we've added electrons to one plate, the other plate becomes positively charged because the electrons are scared away by the negative plate. Okay, once we've connected the two plates together through what we'd say is, closed loop, a circuit, the electron's going to be like, finally, we can spread out. There's some free room. And so our electrons are going to go from high pressure, the negative plate, to low pressure. And we're going to do that by going through our circuit. And as they move, any moving object has kinetic energy. And so the great thing is that kinetic energy can be converted into different forms, such as light energy. Or as we noticed some of us in our voltaic pile experiment, we held our finger down on top. We noticed our finger got warm. We have thermal energy as well. But our electrons and our capacitors and our batteries do exactly the same thing. They go from high pressure, the negative plate, to low pressure, the positive plate. So what is this high pressure, low pressure thing? This is our voltage. Let's get to it. All right, our scientific name for voltage is truly electric potential. This is very similar to electric potential energy. In particular, we said it is the pressure that causes electrons to move through material. High voltage, high electric potential is just a high concentration of electrons. Low voltage and low electric potential is a lack of electrons, maybe through friction, maybe through induction, maybe through contact, maybe through a chemical reaction. Okay, and the volt, named after our friend Alessandro Volta, is the unit of electric potential. Let's see a quick demo so we can see what high voltage and low voltage looks like. Okay, so we have a couple of check questions. Voltage is, go ahead and answer, electrical pressure that causes electrons to move. Question 2, which image has a higher voltage between the plates? All right, the answer is A. Why? There's more negatives here. They really want to spread out. Here, they want to spread out as well, but there's certainly a higher pressure difference between these two plates. Okay, so we have a great way of describing the relationship between voltage, electrical pressure, and current. Okay, let's take a look at what that looks like. All right, so in this squeeze bottle method, we saw that if you push really hard on the squeeze bottle, you put a high pressure, then you get more electric current, right? So voltage causes current, and it's limited by the resistance, the opening of the squeeze bottle. High voltage is high electric pressure, squeezing the squeeze bottle really hard. It causes a big current flow. Low voltage is low electrical pressure. We're not squeezing very hard. We don't get much electric current overall. So when we talked about the voltaic pile, we built a bunch of cells. We said in comparison to a 6-volt battery, a 9-volt battery, a 1.5-volt battery, our voltaic pile had about 80 volts. That was a lot of electrical pressure. Okay, so what about this resistance thing? We talked about insulators versus conductors in the past, and the quantity that describes that is electrical resistance. Just like how open our squeeze bottle was, our materials that are great insulators have a ton of electrical resistance. They really want to hold on to their electrons tightly. And our conductors, like our metals or our salty liquids, they don't hold on to their electrons very tightly, and they pass them along. They'd be like a big open hole at the end of our squeeze bottle. Okay, let's do some check questions. 1, a good conductor of electricity has A, high resistance, B, low resistance. Question 2, a good insulator of electricity has A, high resistance, or B, low resistance. Go ahead and attempt it on your own. Okay, low resistance for a good conductor and high resistance for a good insulator. And we said, what is a great insulator we have on us at all times? Ideally, our skin, right? Okay, here's one other way of looking at it. If you were to talk about just a wire itself, the resistance of the wire depends on what we call the conductivity, and that's really dependent on the thickness or length of the wire. Okay, here's a great way to think about the resistance of a wire, because it turns out resistance will correlate to how much heat you get when you put electricity through a wire, and we'll see that on Thursday in a great experiment. Okay, so imagine you have a very thick straw versus a very thin straw. If you're blowing through a really thick straw, isn't it pretty easy to blow through? Yeah. And if you tried to blow through these little thin straws, you might say, man, Mr. Mellor, I think I need more straws. I can't breathe. It's really hard, right? Yeah. And so electric current is kind of like that. If you have a thick wire, things are great. It's a good conductor. It's easy to pass charge through. If it's a thin wire, it's not so good. You're going to have a lot of resistance. Okay? If the wire is really long, then you have a lot of resistance. If it's really short, you have less. There's just less material for the electrons to pass through. Okay? We measure resistance in the unit ohm. Okay? Electric resistance is measured in ohms. The thicker wire will have more or less resistance than a thinner wire, and a longer wire will have more or less resistance than a shorter wire. Think about your straw example and answer. Okay? And so how do we tie this together? Well, we have a great relationship between electrical pressure, the flow of electrons, and resistance, and we call this Ohm's law. In fact, we say electric current is caused by electrical pressure, voltage, and limited by resistance. This gives us the units of current as the ampere. 1 amp is a lot of current. We said 0.070 amps, aka 70 milliamps, is enough to stop your heart. Yikes. So current is the stuff that's dangerous. Voltage, we see high voltage signs all over the place. That's not dangerous, okay? But voltage supplies the push, resistance opposes the push, and current results. All right, so let's wrap up with a quick practice problem. We'll get to more conceptual stuff next week. What is electric current through a circuit with resistance of 6 ohms and a 12-volt battery? Well, we go ahead and apply this equation. Current equals voltage, 12 volts, over 6 ohms. All right, we have 2 amps. And we think to ourselves, is that a lot? Well, look down here. Can be felt, painful, muscle spasms, loss of control, fatal through heart. This is way larger than any of these. This is enough current to kill you, all right? But you think to yourself, if I touch a 12-volt battery to my hand, or I touch an 80-volt battery to my skin with the voltaic pile, why did that not kill us? Well, our skin's resistance is on the order of 10,000 ohms, okay? So that gives us much less than our amperage needed to kill us, all right? Not too bad. We'll see you next time. Good job, guys. Bye.